computer. There we go. Okay. All right. So let me talk today about atomic mass. So we're looking at section 2.5. And so 2.5 is the issue of the atomic mass scale and the average atomic mass. Okay, so to talk about that, let's refer to the periodic table. I'm going to just put one of the elements that's in the table. The first element in the second row is carbon. Carbon has an atomic number of 6. So remember, the atomic number...
Professor, I can't see anything on the board.
Oh, hi, I'm sorry. Huh. Okay, let me do this. Let's try it again. There we go. Just needed to be refreshed. Okay. So we're going to start by putting the atomic number here. And remember, that's equal to the number of protons in one atom. Okay. But then we're going to have a number down here at the bottom, which is typically, I'll put a couple sig figs here. I'll put a lot of sig figs in there so you can see that, right? This is called the atomic mass. And it's the mass of one atom. So if you were weighing carbon atoms, the weight of one carbon atom is 12.0107. The units are AMU. So it has units, right? These are AMU, which just stands for atomic mass units. Now, some people are a little more modern about this, and they'll put U instead of AMU, and that just means units. So you may see AMU, you may see U, but they don't mean exactly the same thing, but I don't want to go through the technical differences. They're close enough to meaning the same thing that we'll go ahead and use some interchangeable. Okay. That's essentially how much an atom weighs. Okay. There we go. Okay, so it's 12.0107 for carbon. Sometimes you'll just see a few sig figs. So you might see, for example, 12.01. This is when it's just rounded. It doesn't have as many sig figs. And you could see anything in between. It might be 12.011 or as much as 12.0107. But these are not whole numbers. They're not exact values. So it's not, you're not going to see 12. You're not going to see 13. You're not going to see 6. The number down here is an actual measured value, and it's typically a decimal value. Something point something something, okay? But essentially that's how much an atom weighs. Now, what's interesting about these elements is that they're formed in stars. So all of the carbon that's in our bodies was actually formed either in a star or in the atmosphere of the Earth, okay? But the vast majority are formed in stars. And it turns out you can have different forms, right? So for example, we talked about this last time. Carbon has a few different forms. Now, really, there's only 2 forms that you're going to find in nature for the most part. So remember, these are called isotopes, right? Isotopes are forms of the same element. So these are all isotopes of carbon. So they all have the atomic number, right? The atomic number now, when we write it this way, is written down at the bottom. And then we said the number at the top is the mass number. Okay, so this is easy to get confused. There's the mass number, but then there's also the atomic mass. They're not the same thing. So the mass number is the number of protons plus neutrons in the atom. And then the atomic mass is just the actual mass of the atom. Okay, so they're different, but they are related. And what happens is, if you take a look at this number for carbon, it's pretty close to 12, which is pretty close to the mass number of this isotope of carbon. They are actually related to each other. They're not the same thing, but they're related. So what we're going to do now is we're going to do a little calculation to determine how we use these numbers here, essentially those numbers there, to figure out this number here. Okay, so we're going to, using isotopes, we're going to actually calculate this number down here. So I'm going to show you an example. The one I'm going to show you is, do we want to do 10? I don't want to do 10. Let's do a different element. Let's try this one. Oh, that's another one, 10. That's interesting. Oh, wow. Okay, we'll do 10. That's fine. All right, so the example I'm going to show you is with 10. Let me get rid of this. There we go. Okay, let me create a new screen. Okay, so we're going to find the atomic mass. Okay, so the way these problems work is they're going to give you the name of the isotope. So here we go, SN 116, SN 114. Then they're going to give you the actual mass of that isotope, and it's going to be an AMU. So 115.90 and 113.90. Okay, and then they give you what's called the relative abundance. And this will be a percentage. Okay, so there's two things they want you to do. One is to calculate the atomic mass. And then two, they want you to write the symbol. And they want you to write it in the form that it would be in the periodic table. Okay, so this is a calculation. So you're gonna do a little calculation. You wanna have your calculator out for this one. So here's how we do it. This is called a weighted average. So I'm gonna show you a quick little example just to kind of give you the idea of how we're doing this. Suppose I said I have 5 dogs and each one weighs 50 kilograms. And I have 3 dogs and each of these 3 dogs weighs 40 kilograms. Okay, so I've got a total of 8 dogs, right? So suppose I said, let's find the average weight of these dogs. Well, one way you could do that is you could just add them all up. You could say, hey, you know, there's 50, for the first dog weighs 50, the second one weighs 50, the third one weighs 50, the fourth one weighs 50, the fifth one weighs 50. Then we got 40 plus 40 plus 40, and there's a total of 8 dogs, right? And you could add all those up and you'd get the answer, okay? So that'd be one way to do it. Another way to do it would be to say, look, wait a minute, we're adding 55 times, right? Why do it that way? Why not just do it this way? 5 times 50. And then you got 3 at 40, so plus 3 times 40. And then divide that by 8. You get the same answer, right? It's going to work out to be the same. So that would be another way to do it. Another way to do it, though, would be to say, look, we've got 5 of them weigh 50 out of 8, 5 out of 8. So a third way to do it would be to say, look, we got 5 out of 8 times 50. And we have 3 out of the 8 are 40. And you can go through that, but you'll get the same answer. So here what you're doing is you're using a fraction times the weight for the first one, plus a fraction times the weight for the second group, And those 3 different methods are equivalent. Now, I could show you an even fourth way to do it. The fourth way would be kind of based on this last one. You could say, look, 5 out of 8 is 0.625. So this is really 0.625 times 50. And then 3 out of 8 is 0.375. So that's 0.375 times 40. And if you added those together, you'd get the same answer again. So my point is that weighted averages can be calculated in different ways. But when we measure isotopes, what we get, the data that the machines will give us, looks something like this. It tells us the mass of each isotope, how much each isotope weighs, and then it gives us what's called the relative abundance, which is a percentage, okay? So even though we could do a weighted average this way, or we could do it this way, the data that we get from a machine, from an instrument that measures these things, it's not going to be in that form. It's going to be more like in this form right here. So we have to use this calculation right here. So let me show you how we do this. I'm going to, I'm going to erase some of this here, just so that you can kind of see it with the numbers there. I don't want to get rid of the numbers. So let me show you how this is. Pretty simple calculation, but I wanted to kind of show you where it comes from. So typically they give us a percentage and then the atomic mass of each element. So here's how you do it. This is called a weighted average. When we talk about a percentage is a ratio of how many out of the total times 100. So what we do is we take our percentage for the first one, 58, and just write that out of 100. That's what 58% means, 58 out of 100. And you multiply that by the atomic mass for that isotope. Okay, so you take your percentage, divide it by 100, that gives you a fraction, and then multiply that by the atomic mass for the first one. Then you do the same thing for the second one and you add them. So 42 out of 100, that's a percentage, times 113.90. And the units are AMU, atomic mass units. We'll talk more about AMU later on, chapter 3. Okay, so then you add them together. So 58 out of 100 is 0.58 times 115.90. So you have 67.222 AMU. Percentages are not units, so there's no units percentage, so it's just AMU. 42 out of 100 is 0.42 times 113.90. And you get 47.838 AMU. Then you just add them together. Okay, so plus 67.222. And you get 115.06 AMU. Okay, now let's take a look at the sig figs here. We're going to multiply this one right there. Okay, that looks okay. I think that's fine. We got 2 sig figs past the decimal point here. So we have 2 here. That looks good. Okay. So that's our AMU. That's our average atomic mass. This is called the atomic mass. And it's kind of like what I did with that little example with the dogs, right? Now, the last thing they ask you to do is to write the symbol for it. So the symbol for the periodic table, you'd put S in here. Up here, you put the atomic number, which you can just look that up in the periodic table. And then down at the bottom, we put the atomic mass. Okay, so there's our atomic mass. And then up here, we're going to put the atomic number, right? The atomic number essentially tells us where it is in the periodic table. So we go to the periodic table and just look up tin. I think it's 50. I think tin is 50, but let me check. I got it right here. Yeah, it's 50. Okay. So there we go. So there's your answer right there. So two parts to this. One is finding the atomic mass. The other one is just writing the symbol like you would see in the periodic table. Okay. Let me show you another example. It's a pretty simple calculation. You just have to practice them. So let's take a look. I'm going to bring up another Alex one here. So a lot of the examples are tin. Here's one that's molybdenum. So let's do molybdenum here, okay? So again, they're going to give you the isotope name. And like I said, these are formed in stars. So the amounts that you have depend on the whole thing, the whole history of that particular star. So on our planet, all these elements came from some star that blew up a long time ago, billions of years ago. And they're different, it depends on the planet too. So like if you study what these abundances are on Mars, they're slightly different than they are on the Earth. And you can actually tell what planet something came from by looking at these isotopes, these relative abundances. So here's molybdenum. These are the two isotopes that are given. And then the atomic masses are given for each one. So each one has a different weight. Each isotope has a different weight because it has a different number of neutrons. Molybdenum 95 has one more neutron, so it weighs about 1 extra AMU. Okay. And then our percentages, 94.8% and 5.2%. Now, just to kind of think about numbers a little bit, suppose I said that 94% of all the dogs weighed 50 kilograms, and only 5.2% of them weighed 40 kilograms. When you do the average, what you'd find is the average would be closer to 50. Because if most of them weigh 50 kilograms, the average is going to be close to that. It's called a weighted average, right? So same thing here. When we do our weighted average, the mass, the average mass is going to be closer to 93.91 because almost all of the molybdenum is at 94.8. So it'll be closer to that. So again, all you do is you say, so it's called the average atomic mass. You take the first one, doesn't matter which order you go in, but you take the first one, 94.8 out of 100. That's what a percentage is. It's a number out of 100 times the atomic mass. I'm putting a dot here to mean times, and then the dot there's a decimal. And then 5.2 out of 100 times 94.91. If you want to put parentheses around it, you can do it that way. And then you're just going to add these two together. Now, the examples they give you in Alex only have 2 isotopes, but other elements have 3 or 4 isotopes, but I don't think they give you anyone that have 3 or 4. But if you had 3 or 4 isotopes or 5, you just do the same thing. You add each one together. You take the percentage out of 100 times the atomic mass for that isotope, and then just add them all together. Okay, so like I said, we should get an answer that's closer to 93.91 than it is to 94.91 because most of the molybdenum has this weight right here. So let's see, 94.8 divided by 100 times 93.91. So you get 89.027 AMU. And then we do the 5.2 out of 100 times 94.91, and you get 4.935 AMU. So see, most of the number is 89. The first term is 89, and the second term is only 4.9. So it's going to give you a number that's weighted towards this value here. Okay, so 89.027 plus 4.935, you get 93. I'm going to round it to 2 digits past the decimal point. Okay, because this goes 2 points, they each go 2 digits past the decimal point. So I'll put them there. And there you go. So it is 93.96. It is pretty close to this one. It's just a little bit above this one because 5% weighs more. And then they ask you to put the symbol. So to do the symbol, you write the symbol of the element. You put the atomic number on the top. You put the atomic mass on the bottom. Okay, so there's your 93.96. And then is molybdenum, I forget what, is it 52? No, it's not 52. Molybdenum is 42. So there's your atomic, just getting it from the periodic table, okay? Now, when you do these ALEKS problems, they make a point of saying that these problems you're doing are found on a different planet than the Earth. So you may not get the same atomic mass that you get from a real periodic table because the real periodic table comes from the Earth. What they do to get those numbers on the Earth is they take seawater and then they analyze the element, the isotopes of each element in the seawater, and then they get their weighted average, and then they report those numbers on the periodic table, okay? So if this came from a comet or if it came from a meteor, it's going to have slightly different percentages. These vary a little bit, okay? And so you can actually tell there are actual rocks that they find in Antarctica that were embedded in the snow and the ice for maybe even millions of years. And then they do an isotopic analysis of it, meaning they figure out what these numbers are. And what they've discovered is some of those rocks are not from the Earth. They're from outside the Earth. So in the 1970s, they started sending landers onto Mars, and they had these devices that could measure these numbers as well. And what they found is that some of the rocks in Antarctica have the same ratios, the same percentages as what occurs on Mars, which means most likely at some point a large meteor would strike Mars. If you've ever seen pictures of Mars, there's actually craters, right? You got these big craters on Mars like the moon. Meteor strikes Mars, huge explosion. Mars is smaller than the Earth. It has a lower gravity, smaller gravitational pull towards things. So it's possible to eject stuff that escapes Mars altogether and goes out into space. So meteor strikes Mars, blows up some of the surface of Mars, escapes into space. Over time, it sort of orbits the sun. Every once in a while, it crosses paths with Earth, crashes into the surface of the Earth. They're usually not very big. They're maybe this big or maybe this big. Most of the time when they crash into the Earth, eventually what will happen is the rain and the snow will break them down and you can't even tell they're there anymore. But on the Antarctica, because it's frozen, essentially it'll land in the ice, just kind of stay there in the ice. And over time, if you send people down there, you can go look for these rocks and find them on the surface of the ice, take them back to a laboratory, and you find out they're coming from Mars. So it's kind of cool. Okay, so we actually know a little bit about Mars without even going there. You know what the geology is, a little bit of it anyways. Okay, so let me see, is there any that are any different? I don't think they give you any that have 3. Okay, so we'll leave it at that one. There's a ruthenium one. Okay. All right, so that's it for isotopes. So what that does is that it gives us essentially now an understanding of where these numbers come from. So when we say, hey, carbon is 12.011, we now know that atomic mass is an average of the different isotopes of carbon. And if you look at that number, see how close it is to 12? It's really close to 12. What that means is 99% is carbon 12. Almost all of it's carbon 12. And then about 1% is carbon 13. And then 0.0001% is carbon 14. But if you do the weighted averages using those numbers, what you find is that, hey, you're going to get a number around 12.01. So that means in us, in life on Earth, 99% of all the carbon in our bodies, in the proteins and the carbohydrates and the lipids, all of that, 99% of it is carbon-12. But a small percentage of it is carbon-13. There's a little bit of carbon-13 in our bodies, and even a smaller amount of carbon-14. But carbon-14 is unstable, it's radioactive, so it doesn't stick around for too long. But we do have a little bit of radiation that our bodies are producing because we have a little bit of carbon-14 in our bodies. Kind of cool. You can actually learn things about how the Earth operates and how life operates just by studying the carbon-14 that's in our bodies. Okay, it's kind of cool. And trees, it's in essentially all life forms. All right, so that is average atomic mass. The next topic that I would like to do is start talking about ions. The next topic is ions, which is a cool topic. Okay, so let's move on to section 2.6, which is ions and ionic compounds. Okay, so in our bodies, we have ions. We are not just molecules, we're not just compounds, we're actually ions. So for example, in blood, we have sodium ions. I'm going to write it this, well, actually, let me spell it. We have chloride ions. We have calcium ions. We have magnesium ions. We have potassium ions. But we have other ions too. We have something called the bicarbonate ion. We have something called the phosphate ion. And those are just some. There's other ions as well, but these are probably the most important ones in us. In the oceans, sodium, chloride, calcium, magnesium, potassium, bicarbonate, they're all in the oceans as well. So these are important ions. And so let's talk a little bit about what ions are. I'm going to start by looking at kind of the simplest type, which is what is called a monatomic ion. A monatomic. This just means one atom. It's an ion that's one atom. Now, what is an ion? An ion is a charged atom or a charged molecule. Charged meaning electricity. That's the key here. We're talking about electrical properties. So let's remind ourselves that in an atom, you have the nucleus at the center, right? And the nucleus is where the protons are and the neutrons. That's in the nucleus. Outside of the nucleus, you've got these things called electrons. Okay. Now, the electrons have a negative charge, and the protons have a positive charge. So the atom itself is actually a complex system, right? It's like a solar system. It's got positive particles, it's got negative particles. They're related to each other. Overall, in an atom, the number of protons is equal to the number of neutrons. So they balance each other. There's a balance there. But it turns out it's possible to remove electrons. You can remove one. You can take one off. In fact, a battery does that. A battery takes an electron off of one atom and moves it over to another one. We call that electrical current, right? So electrons are being shuttled around, moved from one atom to another all the time. And if an atom loses an electron, it now has more positive charge than it has negative charge, right? So for example, sodium. Let's take sodium. Sodium is element number 11. I'm sorry, it's element number 11, right? Remember, 11 is the atomic number. That's the number of protons. So it has 11 protons, P plus for protons, and it has 11 electrons. But it turns out it's actually pretty easy for molecules to take one electron off of a sodium. You just rip it right off. The electron is further out from the nucleus, so it can actually be pulled off. And so a sodium ion is the case where you take off one electron and you only have 10 electrons. That's called a sodium ion. And the sodium ion has more positive charge than it has negative charge. So here's how we represent that. We represent it by putting the symbol Na for sodium, and then we put a positive to the right as a superscript. And that's how we indicate that this is a sodium ion as opposed to a sodium atom where we don't put the positive charge. There's no positive, obviously. Okay? So ions are charged atoms. So the sodium ion would be written as Na+. Now, this happens all throughout the periodic table. Almost all atoms have the ability to form ions. And there are patterns to them. And so let me show you what the first pattern is. If you look in the first column, hydrogen, lithium, sodium, potassium, rubidium, and cesium, they tend to form +1 ions. That just happens in nature. They lose one electron and they form a charge of +1. So how would we write them as ions? We would say, oh, H+, Li+, Na+, K+, Rb+, Cs+. So all of those are just the forms of these ions, okay? These are the symbols for the elements. These are the symbols for the ions. And that first column in the periodic table, they tend to form +1 ions. So when we say, hey, you have too much sodium, you're going to get hypertension, we don't mean sodium atoms. We mean sodium ions. Because in blood and in interstitial tissue, interstitial fluids, the form of sodium that exists is actually the ion, the plus ion. And same is true for potassium. When it says, hey, you need to have more potassium in your diet, or you need to have less potassium in your diet. We don't mean potassium, the element, the atom. We mean potassium, the ion. That's actually the metabolic form of potassium. Same with magnesium, all of them, okay? Second column, they tend to lose 2 electrons. So beryllium, magnesium, calcium, strontium, barium, they tend to lose 2 electrons. Okay, so what does that mean? That means the symbol would be Be. Now, when you do symbols for the charges for these ions, you put the number and then the symbol for the charge. So you put 2+, not +2, but 2+. The next one below that is Mg. So Mg 2+, Ca 2+, Sr 2+, Ba 2+. So second column, they tend to form +2 ions. Generally, that's the form that they're going to be. So magnesium, when they say take more magnesium in your diet, or you need more calcium in your diet, they don't mean elemental form. They don't mean calcium like this, or strontium like this, or magnesium like that. They mean +2. +2. You need the ions in your diet. Okay. So first column, second column. There's a similar pattern all the way on the other side of the periodic table. So there's helium, then neon, then argon, then krypton, then xenon, and then radon. We're going to ignore those. Those are called the noble gases. They do not tend to form ions except under extreme circumstances. Huge electrical voltages will cause them to form ions, but not simple things like putting them in water. So we ignore those. But next to those is F, Cl, Br, and I. And these have a pattern. They tend to form -1 ions. Okay, so how would we write the symbols? F minus, Cl minus, Br minus, I minus. -1 ions, okay? We're going to talk about naming when we get to that. We're not to there yet, but next time we meet, we'll talk about naming. So these are ions as well. But notice these are negative ions, right? So on the left side of the periodic table, they're positive, which means they lost electrons. On the right side of the periodic table where the nonmetals are, they're negative. So that means they gained electrons. The electron is negative. So if you gain an electron, you become negative. The next column over, oxygen, sulfur, selenium, tellurium. These ones form -2 ions. So they would be written like this. Remember, you put the number, then the symbol for the charge. So 2 negative, 2 negative, 2 negative, 2 negative. Next column over, -3 ions. So that would be nitrogen, phosphorus, I'm sorry, yeah, phosphorus, and then arsenic. Sorry, a little mental freeze there. -3, that means they gained 3 electrons. So N3 minus, P3 minus, AS 3 minus, okay? So there's some patterns, and it would be nice if there was like a cool, simple pattern for the entire periodic table, but there is not. So these are really the only patterns that I can give you right here. First column, each atom tends to lose 1 electron and form a +1 ion. Second column, group 2A we call it, right? We call this one group 1A and then group 2A. They tend to lose 2 electrons to form +2 ions. Then you got to go all the way to the other side of the periodic table. This is group 7A, 6A, 5A. That's one of the reasons we talked about that last week was the periodic table, so you can kind of label these things. -1, -2, -2. That means they're gaining electrons. So there is, in general, a pattern that the elements on the right side of the table tend to gain electrons, and the elements on the left side tend to lose electrons. So you generally don't see potassium with a negative or a chlorine with a positive. It's possible, but not generally. You don't see it very often. So the negatives are on the right side and the positives are on the left side. It's kind of cool, kind of simple. Okay, so let me show you an example here. I want to show you a problem. So what they do is they give you a symbol. And then they ask you, is this an atom or is it an ion? And then they ask you for the number of protons and then the number of electrons. Okay. So let's go through. Oh, actually, I'm sorry. So they give you 3 options. Is an atom an ion? And then they say, is it an atom, a cation, or an anion? Okay, so there's 2 different types of ions. That's an easy issue, though. We can deal with that easily. Okay, a cation is positively charged. An anion is negatively charged. Okay, positive or negative, cation. All right, so let's take a look. What you do is you look at the symbol. Look at the symbol. It's negative, right? That means it's an ion. If it doesn't have any charges, then it's not an ion, it's an atom. But if you see a number there or a charge, that means it's an ion. So we know it's an ion. Is it positive or negative? It's negative. So that means it's an anion. That's easy. Okay. The next thing, though, is the number of protons and electrons. So how do we do that? What you do is you look for the symbol in the periodic table. So if you look for arsenic, As, you'll find that it's number 33. Okay, it's got 33. Remember, that's the atomic number. And that's the number of protons. So there we go, 33 protons. That's easy. You just get that right from the table. But the electrons, you have to do a little bit of calculation. So here's what you do with the electrons. If it's -2, that means it has 2 extra electrons, right? Each electron's negative. So if it's -1, that means you have 1 extra electron. If it's -2, that means you have 2 extra electrons. If it's -3, that means you have 3 extra electrons. So what you do is you say, okay, it's got to have 33, but it's got an extra 2. So you just say 33 plus 2, and you get 35. Okay, and that's what an arsenic ion is. It's an atom of arsenic that has 2 extra electrons. Now, we're not going to go through that in this course, but when you go to the next course, Chem 11, what they do is they talk about where those electrons go. Where do the extra electrons go? And then you can actually write these little diagrams to show all of the electrons. It's kind of cool, but we don't do that in this course. So let's take a look at another one. Let's say we have this one. I'm going to give you a slightly different piece of information. In this case, I'm not going to give you the symbol, but I'm going to ask you for the symbol. And then I'm going to say that it's an atom. Oops, sorry. Let me just check something here. There we go. So I'm going to tell you it's an atom. It's not a cation or an anion. It's an anion. It's an atom. So we know it's an atom. Okay. And then they're going to give us the number of protons is 41. And then we have to figure out the number of electrons. Okay. So this one's, it's like a little matching game. It's kind of cool. So here's what you do. It's an atom. Now, an atom, the protons is equal to electrons. That's what an atom is. The two are equal to each other. So if they're equal to each other, we also know this has 41 electrons. Okay. Now, if it said it's a cation, that's a little different, right? If it said it was a cation, then we know we have a different number of electrons or protons. But in this case, they tell us it's an atom, so we have the same number of electrons. The next thing is, how do we get the symbol? Well, again, there's the 41. That's the atomic number. Protons is atomic number. So if you know the atomic number is 41, you just look it up in the periodic table. Just look for symbol 41. So you go to the table. 41 is, I'm looking at the table right now, is an NB, which is called niobium. Okay, so you just look in the periodic table. So you want to have one of those handy. Make sure you got a table handy. So the symbol would just be NB. And then it's neutral, right? Its protons are equal to electrons. So we don't have to have a charge here. We're just going to write NB. And that would be your symbol. Now, if we knew that it had extra electrons, we would put the charge next to it as well. But in this case, they just tell us it's an atom. Okay. Let's take a look at another example. So here's one. In this case, they don't give us the symbol, but they want the symbol. They don't tell us whether it's an atom, a cation, or an anion, so we don't know that either. But they do tell us the number of protons is 12, and the number of electrons is 10. So, there's a certain amount of info you need. Okay, so here's how we'll go about this. First of all, this is the easiest part. This is the atomic number. If you know that number, you can look it up in the periodic table. So number 12 is magnesium, Mg. You just look that up in the table. So you know that right there. Now, is it a cation, an anion, or a atom? It can't be an atom. These numbers are different. If those numbers are different, it can't be an atom. In an atom, they're the same. So we know it's either a cation or an anion. Now you just kind of reason through this. What we know is that it has 10 electrons and 12 protons. So here's the way I do this. I say, look, 12 protons means plus 12. 10 electrons means minus 10. So if you add those together, the positives and the negatives, what do you get? You get plus 2, right? There's more positive than there's negative. If it's positive, that's a cation. Cations are positive. So now we know it's Mg, but we also know the charge. But remember, when you write this in, you got to put the number first and then the symbol. So you put the number in 2 and then the symbol plus. Okay? So more protons, fewer electrons, it's going to be a cation, which is going to be positive. Okay? Let's see. Okay. That's relatively simple. Scandium. Okay. So the next one, I'm going to do one more. Okay. So this is where you're predicting ions formed by common main group elements. Okay, and then we'll end it here. So in this type of problem, what they do is they give you a symbol. I'm sorry, they give you the name. And then they want you to write the symbol. And then they say, is it a cation or anion? And these are the key to this is that it's main group elements. So when you do this problem, it says main group elements. Okay, that means pull out your periodic table. You're going to pull out the periodic table and you're going to look to see where these elements are on the periodic table. Okay, so for these ones, it's going to be those elements that I just went over a couple of minutes ago. So let me rewrite them. H, Li, Na, K, Rb, Cs. Remember I said these are all plus 1? And then I said the second column, these are all plus 2. And then I said all the way over here, so that's group 1A, group 2A, and then group 7A was F, Cl, Br, and I. These were minus 1. And then group 6A was O, S, Se, Te. These were minus 2. Okay, same idea here. So they're going to give you the elements of those ones that I just told you about. Okay, so cesium is right there. Okay, so is that a cation or an anion? It's positive, so that's a cation. What about the symbol? The symbol, you write Cs, and then what's the charge? Plus 1. But in chemistry, this is often confusing. In chemistry, if something is 1, you just write the symbol for the charge. You don't write plus 1 or 1 plus, you just write the plus. So you just write plus. Okay. And then oxygen is over here. So that's an anion, right? The anions are over here. These are the ones that are negative. The cations are the ones that are over here. These ones are positive. So this would be an anion. And then you write the symbol O, and then it's in column 6A, so minus 2. But remember, you put the negative after, so you put 2 minus. Okay, it means the same thing. Minus 2 is the same as 2 minus, but we have certain notations in chemistry where we write the number and then the symbol. It's just the way we do it. Okay, let me show you one more. Let's do iodine. Okay. So iodine, you look that up, Iodine's right here. There it is. So the symbol is I. It's in column 7A, so it's -1. So you just put a minus. Okay. And then it's on this side, it's negative. So that's an anion. So those are pretty easy. Those are not that difficult. What gets more interesting is when we start looking at compounds of ions. So right now, all I've done is kind of gone you through sort of the basics of what ions are and how we write the symbols. But when we get to the next topic, which we'll do next time, is we're going to talk about ionic compounds. And that's where it gets interesting. Because what happens is if you take a positive ion, a cation, right? That's an ion. And you combine it with an anion. Okay? They will combine to form an ionic compound. A compound, if you recall, when we went back to chapter 1, was one of these substances that had 2 or more elements in it. So here's one right here. That's an ionic compound. It has 2 elements in it. And what happens is this positive charge and this negative charge neutralize each other, meaning they cancel each other. They're attracted to each other through electrical forces. In nature, if something is positively charged, it will be attracted to something that's negatively charged. It's kind of cool, right? So that attraction, it holds the atom together, right? Because remember, a proton is positive and an electron is negative. So they're attracted to each other. The same is true for these compounds. It's the same physical force. The positive charge of the sodium is attracted to the negative charge of the chloride. So those 2 ions will form a compound. It's kind of cool. All right. So we'll get into that next time. Ionic compounds, and we'll learn how to name ionic compounds. And that's really the kind of what we're leading up to in this chapter, is this idea of naming compounds and figuring out what their formulas are and all of that. But the basics of this is an important issue, which is particularly those of you that are biology or chemistry majors, knowing the difference between sodium and the sodium ion. They are different substances. Sodium, a neutral atom. Sodium ion is a cation. The fact that the sodium is a cation is going to give it very different properties. And our cells are evolved to take advantage of the fact that they're ions. The positive charge allows them to get through what these little things are called transporters and cool proteins that are in the cells. It's really amazing stuff. Okay. So we'll talk more about that next week. And if you have any questions this week, reach out to me, and I will be around this week. And good luck with all your problems. Good luck with everything. And I will talk to you later.
Thank you. Thanks, Professor. Bye.
Absolutely. Bye-bye.